My name is Maciej Dunajski. I'm a fellow of Clare College and the professor of mathematical physics at the University of Cambridge here. And I'm delighted to be able to share a story about geometry with you. Geometry is at least 2,500 years old. It's the oldest branch of mathematics within which the concept of a proof has first appeared and evolved. But despite how old it is, I want to start, just adjust my settings. I want to start with something which is even older, and that's the Great Pyramid of Giza. It predates geometry by another 2,000 years, and it's so old that we, people, scientists, had the chance to have a very good look at it. And one thing which was noticed in the 15th century is that if you take the circumference of the base of this pyramid and you divide this by the height, then the number you get is very close to pi. It agrees with pi up to 2 digits. And that suggested to some that perhaps the Egyptian constructors knew the value of pi and that concept before the Greeks did. Another thing which was noticed later was that if you take the height of this pyramid and you multiply it by 150 million, so then you get a distance between the Earth and the Sun. And that suggested that the pyramid might not have been built by the Egyptians, but perhaps by extraterrestrials. And there are several theories like that have evolved since then, and there are people who still take pleasure in noticing various facts about numbers. But while I think this is all pseudoscience and fiction, and even the bit including pi, it's fair to say that whoever constructed this monument must have known what they're doing. If you start throwing bricks in the middle of the desert, you're not going to build anything like that. So some what we would refer to as geometric concepts must have been known to the Egyptians and the Babylonians at the same time. But although this might have been the case, the geometric statements were established empirically, and correctness was not measured by proofs, which was what we would demand now, but by accuracy. So how accurate the statements were. So people would have known how to quite accurately measure a volume of grain in a container, but they wouldn't have bothered or tried to establish a formula in our sense of the word for what this volume is. And they're familiar with the concept of a line segment, but they would have identified this with a piece of string or a path. So the abstract concepts of pure mathematics were not distinguished from real objects. And what was missing were, statements, we would call them theorems today, which apply to all pyramids, or all triangles, or all cylinders, not just one, which you're looking at. And this, so let me give you an example of such a statement together with its proof, and that's a Pythagorean theorem, which tells you that for any right-angled triangle, a square of the hypotenuse C is equal to the sum of squares of the other two sides. Now, there are many proofs of this theorem, and the one I'd like to share with you is purely geometric in that you don't need any formula to write down, and yet the proof is rigorous. So, and I'm not saying it's obvious, but if you look at the two squares I have, you see that the triangles with sides A, B, and C on the left-hand side can be rearranged into 4 triangles on the right-hand side, so that indeed C squared is equal to the sum of B squared and A squared. right? So that's a proof. Now, before you prove this theorem, or indeed any other theorem, you need to decide what the rules of the game are. So what it is you can assume before you make deductions. So I would say what you need is a set of axioms or postulates. And such a set of axioms is credited to Euclid of Alexandria, who listed them in his 4th century BC series of books, the elements of geometry. It's fair to say it's not only Euclid's work, it's also work of his teachers and contemporaries, but he has really put this all together. So let me, there are 5 of these axioms. Let me list them for you and go through them very briefly. The first axiom states that exactly one straight line segment might be drawn between any 2 points. And these are axioms about geometry of a plane. Second axiom is that if you take this line segment or any other line segment, you can extend it indefinitely to a line, straight line. The third axiom, a circle may be drawn with any given radius and an arbitrary center. That is, if you specify a radius, and this is something you will be familiar with from school, A-level GCSE mathematics, if you specify, you probably tend to think of this in Cartesian coordinates, not the way Euclid did, but in our language, if we specify x and y coordinates of a center, and we specify the radius, there is a unique formula you can write down for a circle. Euclid thought of it more geometric. The fourth axiom, a bit odd. It says that all right angles are equal. What does that mean? If imagine a couple of right-angled triangles on the plane, and they translated and rotated with respect to one another. This axiom says that if you take one of these triangles, there'll be a rotation of it, and you can compose it with a translation, so that although the triangles might be different, the right angles will coincide once you slide one onto the other. And finally, the fifth axiom, which has a name of a parallel postulate, is the following, and I illustrate this with a picture. If you take a line L and you take a point P, not on the line L, then there is exactly one line, it's a lighter line on my picture, which contains the point P and doesn't intersect L. So reformulating, for any given line and any point not on the line, there is a unique parallel line which goes through the point. Now, having formulated these 5 axioms, and we'll return to why are there only 5? Should there be more? Should there be less? But for now, let's say that these 5 are given. The task of the mathematician is then to build other statements, theorems, using these axioms and laws of logic. So let me illustrate that for you with a fairly obvious statement. So 2 distinct lines on the plane meet at most one point. You see, well, it's probably obvious to you because you can take pen and paper and experiment with lines, and that's what you'll find. But it's important that this is not part of our axioms. So if it's true, we should be able to deduce it from the axiom. And I'm going to prove it using proof by contradiction. So it was noted by G.H. Hardy, a great 20th century Cambridge mathematician, that this proof of contradiction is can be compared to a gambit in chess. In chess, those of you who play chess would know that you can sacrifice a pawn or a piece to eventually win a game. In a proof of contradiction, one goes much further. A mathematician offers the whole game. So we say we want to prove something, but we say let's assume it's false, and see what happens. If we reach a contradiction, then it must be that what we want to prove is indeed true. So how would it work for our statement? Well, if the statement is not correct, then there are at least 2 points, called them P and Q, in which the 2 lines meet. But then there exists at least 2 lines through P and Q, but this contradicts the first axiom of Euclid, which says that any 2 points can be connected with a unique line segment. So if we believe, or if we accept the axioms of Euclid, our theorem has also got to be true. Now, so let's go back to these 5 axioms and let's focus on the last. You see, in logic, in mathematics, it's important to say only as much as you have to say without repeating yourself. And in axiomatics, that means that your axioms should be independent. That is, if, for example, if it were to be the case that the first 4 axioms implied the 5th one, then I shouldn't have listed the 5th one in my list at the first place. And for centuries, in fact, for millennia, it was suspected that the last axiom of Euclid, the one about parallel lines, could in fact result from the first 4 axioms. And in fact, there are many attempts to prove it. All these attempts turned out to be false because it was established, but only in the 19th century, that there exists a type of geometry, which I'm going to tell you about now, which satisfies the first 4 axioms of Euclid, and yet it does not satisfy the 5th, which means that the 5th one has to be independent of the first 4, because otherwise it would have to hold in this geometry. So this geometry goes under the name of hyperbolic geometry, and it's historically the first example of what we now call the non-Euclidean geometry. So the arena for this geometry is a disk. I'm going to call it D. It goes under the name of Poincaré disk, although it was an Italian mathematician Beltrami, who had it a few decades before Poincaré. So it's a disk of Euclidean radius 1, and it's bounded by a circle, but this circle, the boundary circle, is not part of our disk. It doesn't belong to the geometry. Now, to be able to talk to you about the 4th and 5th axioms of Euclid, I need to tell you what plays the role of straight lines and line segments. So that they called hyperbolic lines in hyperbolic geometry. See, according to Euclid's first axiom, we should be able to connect any 2 points by a line. So how do we do it in this non-Euclidean geometry? Well, there are 2 possibilities. If the 2 points lie on the diameter of a circle, then the line segment connecting them is a part of a diameter, and this diameter can then be extended to the whole diameter. But generically, the 2 points you want to connect would not be on the diameter. And then what you do is you construct a segment of a circle which contains the 2 points you want to connect. Maybe this point I'm calling P, you might just about see that, and some other points. And this circle has to intersect the boundary of our disk at 90 degrees. And you could convince yourself, even within your knowledge of mathematics, that there is a unique such circle with this property. So a unique circle inside the disk containing any given 2 points and cutting the boundary at 90 degrees. And you see, once you construct these hyperbolic lines, you can then think of other geometric figures like triangles. So for any 3 points, these 3 points here, you can connect any pair of the points by a hyperbolic line, and what you get is a triangle. So it turns out that these hyperbolic lines satisfy the first 4 axioms of Euclid. It's also the case that these lines minimize a notion of a distance. It's not the Euclidean distance. You see, on the plane, Euclidean plane, straight line segments are the shortest connecting any 2 points. So you can prove, and this is far less obvious, we teach it to our students in the second-year geometry course. You can prove that if you declare a distance between points P and Q to this formula, so to make sense of this formula, you connect P and Q by a hyperbolic line, and this hyperbolic line intersects the boundary at 2 other points, called them A and B, and then you compute the length of Euclidean length of segments AP, BQ, AQ, BP. You construct this ratio and you take its logarithm and you declare this to be the distance between P and Q. And what we'll teach you, or somebody will teach you if you end up studying mathematics, is that if that's how you define the distance, then these hyperbolic lines, which I defined for you, are the shortest with this distance. See, then you can also make sense of this pictorial representation of the hyperbolic disk, which is due to Dutch graphic artist MC Escher. On this picture called Circle Limit 4, presented hyperbolic geometry and the disk full of white angels and black demons. And you see, as on the picture, as you get closer to the boundary, the demons get smaller and they appear to have a smaller area. But in fact, if you instead use the hyperbolic distance to compute the length and the areas, you'll find that the size of each demon from head to tail is the same for all the demons on the diagram. It is just that the small ones are far apart, so they seem smaller to us, but they're the same with the hyperbolic distance formula. It also follows from this logarithmic formula that the boundary circle is infinitely far away from the center of the system. Right? So that's not how we see it, but we essentially were being fooled by our Euclidean intuition. But now I need to convince you that this is really a non-Euclidean geometry. So that although the first 4 axioms hold, the 5th one fails. And remember, the 5th axiom says that for any given line L and any given point P, there should be a unique line containing P and not intersecting L. But in this hyperbolic disk model, there are infinitely many such lines, and I've drawn a few here for you. They all have a property, they all hyperbolic lines, because they have circles intersecting the disk at 90 degrees, and they contain P, and yet they do not intersect L. So it's a non-Euclidean geometry, and Euclid was right. After all, you have to add the Euclid's 5th axiom to the first set of 4 to single out what we now call the geometry of Euclidean plane. Now, given that this geometry differs from that of a plane, we can ask in what other ways it's different and what other theorems hold or carry on from Euclidean geometry to the non-Euclidean one and which fail. And you should be suspicious of any theorem where you have used the 5th axiom to produce a proof. I mean, it doesn't yet mean that the theorem is false because maybe there is another proof. But if the only proof you can think of is based on the Euclid's 5th axiom, and this axiom doesn't hold, then the theorem might fail too. So one such set of concepts and theorems has to do with plane tilings, sometimes also called tessellations. So what's a tessellation? It's a way of covering a whole plane by a collection of shapes. And not all these shapes have to be identical, but we might have few types of shapes, 1, 2, 5. And then with these shapes, we can cover the whole plane without any gaps. Here I've listed 3 examples of tessellations for you. The first one is an example of Islamic tessellation. It's a Moroccan mosaic where you've used 5 different shapes and to cover a plane. And not only you can do it, but it's done in a periodic way. That is, if you've covered a large segment or a segment of a plane, you can just repeat your pattern and that will cover the whole plane. The second example, a familiar example of a regular and periodic tessellation is tiling of a plane by regular hexagons, which here is illustrated on a plaster of honey. Right, again, if you have covered this one plaster, you can then repeat it and that will cover the whole plane. It's interesting that there are other types of tessellations, they called aperiodic tilings, and they were kind of popularized and explained by Roger Penrose, and this tiling I'm giving you here by 2 shapes of rhombi is an example of a Penrose tiling where it is the case that you can cover the whole plane by objects of the same, by 2 types of rhombi of the same angles and sides, but you cannot do it in a periodic way. That is, however large portion of a plane you've covered, millions of square kilometers it might be, it is not the case that you're going to get the whole covering by repeating pattern. You have to, the way you add the tiles on both ends of your tiling is of non-local, and you're not going to succeed by repeating what you've done so far, although Penrose tells you you can succeed and you can cover the whole plane in theory. But so this Penrose tiling, it deserves its own lecture alone. I want to focus by this tiling by regular hexagons. Well, you can ask how many different types of tilings by regular shapes there are on Euclidean plane, and it turns out there are only 3. You can tile by squares, you can tile by hexagons, or you can tile by equilateral triangles. And you can prove, and that proof requires the 5th axiom, you can prove that you cannot do anything else. Now it turns out not to be true in non-Euclidean geometry on the disk. You can cover it with regular shapes of arbitrary numbers of sides, and here I'm showing you the covering with regular heptagons. And well, you might object at this stage, because if you look closely at this picture, you will see that the heptagons closer to the boundary look different, very smaller, and some sides are shorter than others than the one in the middle. But again, this is an illusion caused by our Euclidean intuition. These heptagons are in fact all the same. They have the same sides and the same area if you use the notion of hyperbolic distance and not the Euclidean. And there are many other differences between hyperbolic, non-Euclidean and Euclidean geometry. And the last one I want to tell you about has to do with curvature. In fact, I will introduce the concept of curvature to you. And so here I want to motivate this concept by looking at triangles. You'll know that on the plane, any triangle, the sum of angles is always equal to pi, or if you prefer, 180 degrees. It turns out that on the hyperbolic disk, if you define the triangle as I did, that is for any 3 points A, B, and C, you're going to draw 3 hyperbolic line segments between them. the sum of these angles will be smaller than 180 degrees, whatever triangle you choose. On the sphere, on the surface of the sphere, on the other hand, for any chosen 3 points A, B, and C, you connect them by the shortest lines, shortest on the sphere. These shortest lines on the sphere end up being segments of great circles, so equatorial circles. Then you find that the sum of the angles is always greater than 180 degrees. So there is this motivated thinking that there should be some property of non-Euclidean geometries, of which a sphere is another example, which can be measured by seeing how the sum of angles in a triangle deviates from pi. And there is indeed such a concept. It's called curvature, Gaussian curvature. It was explained and formalized by Gauss. And it can be defined not only for irregular surfaces like the disk or the sphere, but also for surfaces like that of a donut, which kind of looks different and they curve different in the colloquial way at different points. And what you do is the following. You pick any 3 points on the donut and you construct, let's say they're close to each other, and you construct a triangle, add up the angles and subtract pi or 180, well, let's work with radians. So you subtract pi from the sum, and you divide this by the area of the triangle. Now, imagine that your points get very close together, so they essentially converge to 1 point. Well, to make sense of this, you have to use calculus, have to use concept of a limit, because you will divide something which tends to 0 by something else which tends to 0, but Gauss could do it, and if that's done, you'll find that to any point on this donut, you can associate a number, and that's its Gaussian curvature. Now, it so happens that on the sphere of radius 1, the Gaussian curvature is the same, everywhere the same, and positive. On the hyperbolic disk, the Gaussian curvature is everywhere the same and negative, right? But on general surface, like that of a donut, it'll be positive in some regions and negative in other regions. Now, okay, so let me now try to relate to the title of this lectures, 4 Facets of Geometry. I want to make a transition to the third facet. See, the first one was Euclidean geometry with Euclid's axioms and plane and proofs by contradictions. The second one was moving beyond Euclidean geometry, where you drop one of the axioms or keep the other 4 in the case of the disk. That brings novel features. For example, the curvature. The third manifestation of geometry I want to share with you very briefly, although we devote a few lecture courses in our Cambridge Tripos to it, is a link between geometry and mathematics in general and universe, theoretical physics. And I want to tell you about the curvature, and this is the same curvature I defined for the donut, but now applied to the whole universe. See, a donut is a 2-dimensional surface. It's this number of dimensions you can think of for now as the number of degrees of freedom. So the plane is 2-dimensional because any point on the plane, once you've picked a coordinate system, any point on the plane you can specify uniquely by selecting its 2 coordinates. The same sense, space is 3-dimensional. Well, according to Einstein's theory of relativity, the universe, space-time, is 4-dimensional, and these dimensions consist of 3 space and 1 time. And one of the great insights of Einstein was that what we think of as gravitation, so massive bodies attracting other massive bodies in the Newtonian sense, and thus curving their trajectories, that is a manifestation, an effect of the curvature of this four-dimensional space-time. So in the geometry of this space-time, comets and planets and galaxies, they actually move on shortest paths. We call them geodesics, but these are shortest paths with respect to some other notion of distance, a bit like this hyperbolic distance, rather than the Euclidean distance. And Einstein has, in his theory, summarized the connection between gravitation and curvature in a set of equations, very complicated, well, fairly complicated differential equations, which I'm going to symbolically write for you as mass equals curvature. So the more mass you insert in a region of the universe, the more curved this region will be. Now, we now know both from astrophysical observations and also from groundbreaking theoretical work of Roger Penrose and later Stephen Hawking, then that there exist regions of the universe, and they have to exist, such regions, if Einstein's theory is true, where the curvature is infinite. And we now know of two such types of regions. One is what's called black holes. So these are physically, black holes are the final stages of evolutions of certain massive stars, which collapse under their own gravity, and they become very, very dense, so very massive, and the mass is concentrated in small volume. And eventually the space-time becomes so curved that even light cannot escape from the regions of this curvature. So this is colloquially described as a black hole, because there is nothing to be seen, because no light can emerge from this black hole horizon. But importantly, and that's the result of Penrose's theorem, inside this black hole, there'll be a region where curvature is not just very big, it is infinite. Another such type of region is Big Bang, which we think of as the beginning of the universe, which initially was concentrated maybe in a point with infinite curvature. Now, you see, neither mathematics nor physics, as we know them, deals with infinities well. So it's fair to say that physics, at least as we know it so far, breaks down at this infinite curvature point. So that's yet something we teach to students. There is a third-year course on general relativity, which brings geometry and physics together. But that's the first facet, third manifestation of geometry. Now let me finish off with the last one, which is my personal favorite. It goes under the name of projective geometry, and it's a geometry of perspective, geometry of Renaissance art. And to motivate this, I'd like you to look at and compare these two paintings. One is a late medieval painting by Lucio di Buonisiena, the capture of Jesus, where you see Jesus, apostles, people, and you also see trees. And the trees are bigger than the people. And that is true, because in real life, a tree is old enough to be bigger than a person. Except that that's how things really are, but that's not how you see them if you look at an image or if you look at reality. Right? The second painting, Canaletto, shows a church which is far away from a balcony from which the picture is where the picture must have been painted, and this balcony is bigger than the church on that picture, although really we know that the church is bigger than the balcony. But what happens here is we look at this from artist's perspective. So how do you make sense? Can you make sense mathematically of this concept of a perspective? And to do that, so in what sense, in other words, in what sense the geometry of a painting may be taken from several perspectives differs from the geometry of the Euclidean plane. And turns out what you have to do is you need to attach a line, we call it a line at infinity. It's also called the horizon. You have to attach this line to the plane first, and then you'll have the projective plane where projective geometry takes place. So what is this line? Well, imagine first one road with parallel sides, and all these sides, if you look at the straight road, will converge at one point, let's call it Z. Now imagine another road, and it has its own parallel sides, and they converge in some other point at the horizon, call it O. So far, no kind of surprise here. But what's remarkable and might be surprising if you think about it, that if you take a third road, or in fact, as many roads as you want to, then the sides of this third road will also converge at the point. And moreover, all the points on the horizon lie on one line. Okay, so it's sufficient to add this one line to the geometry of the plane to encapture perspective. Now, how would we do it formally? How do mathematicians do it? Well, see, imagine projecting one plane, pi1, to another plane, pi2, from a point. Okay, so this would be looking at the same image from two perspectives. Now, how do we define the projection? Well, let's say you want to project point P from pi1 to pi2. We're going to draw, so these are planes in space. We're going to draw a line which connects P and O, projection point. And this line will then intersect the plane pi2 in the point Q, and this point Q we declare to be the image of P. And we can do it for most of the plane pi1, but we're going to miss a whole line. So we're going to miss the line, you see this line of intersection of a plane pi1 with a plane containing O, which is parallel to pi2. And that's because if you take any point on this, on this line, and you connect with O, it's not going to intersect pi2 anywhere. So the fix is to add this line to the plane pi1, and that way the whole plane pi1 will project to the whole plane pi2, as long as you also add another line to pi2. So if you extend these planes by attaching lines, they projectively equivalent. You can project one of them to the other uniquely without missing anything out. Well, you can then ask what theorems in geometry, if any, so I'm looking at the chart as well, maybe I shouldn't be, it's always interesting to look at the chart. What theorems in geometry, if any, are remain true if you project geometric statements from one plane to the other. Pythagorean theorem, for example, is false. There is no notion of area in projective geometry and no notion of distance either. If you want to see that it's really false, take a right angle, draw a right angle triangle and color the squares so that they add up to each other, and put it a few meters from where you are and start moving around, and you'll see that neither the right angle triangle looks right angled anymore, nor that the squares add up to each other. It's a question of perspective. I mean, from one perspective, one square will be bigger, from another one, another will be bigger. So that theorem is not true. Turns out that the concept of a circle doesn't make sense either in projective geometry. If you start projecting circles from between planes, you find that they become ellipses. So ellipses are okay. So so let me finish off with a statement of a theorem, a very remarkable theorem, which is true regardless of what projection you take. It's known as the Bryanton's theorem, which says the following: if you take an ellipse on the plane, and you consider a hexagon circumscribed about this ellipse, and you label the vertices of this hexagon by A, B, C, D, E, and F, then the diagonals connecting opposite vertices all meet at a single point. Okay? And this is true, this theorem is true regardless of what perspective you take. For a mathematician, the subject projective geometry is part of it is looking for such theorems which are true not in Euclidean but also in projective geometry. See, turns out, if you think about it, every theorem in projective geometry is also true in Euclidean geometry, but the converse is not true. So this Bryanton's theorem is an example of something which holds. So that brings me to an end. 4 facets of geometry. The Euclidean geometry, still very accurate geometry of everyday life, axiomatized by Euclid. That's the geometry you learn at school at the moment, and you will learn in the first year at university. Then hyperbolic geometry, which is one of many examples of non-Euclidean geometries where one or more axioms of Euclid do not hold. Then there is this connection with physics, geometry of the universe, which I very briefly illustrated on an example of space-time, but there are other manifestations of geometry in physics, and it might be that if we ever build a final theory of physics, a unified theory of all interactions, it might be that it will be geometric in its core. And finally, the projective geometry of Renaissance painting. Now, I think I only had one formula in my lecture, but so some of the statements I've made, they can be proved easily. I've skipped the proofs, but if you're interested, have a look in this book, which is aimed at level, I think, slightly below yours. I mean, the readership is that of GCSE maths educated people, whereas you aspire to be professional mathematicians. Anyway, thank you very much for staying with me long, and that's where I stop.